Alrighty, so let's have a look at the June 2014 Applied Physics section of the Unit 5. So let's start off, we've got a motor being used to lift a load, and we've been given some information about the different properties of the system, and it wants us to show that the drum turns through 40 radians as the load accelerates. So what have we got? So we've got initial speed of 0 going to 2.2 meters per second. Got the height change of 3.5, and then it's going to continue at this speed here. Okay, so what other information we have? We have I that's given up there. We've got the mass, or a weight force, and we've got a drum of radius 0.88. Okay, so if it's going to rise by a height of 3.5 meters, essentially the total rotation distance of the drum must also be 3.5. So if we want to turn that into the number of rotations, so the number of revolutions is going to be 3.5, and we're going to need to divide that by 2 pi r, which is 0.088. Essentially we've got the circumference, and so essentially we're calculating the number of circumferences that pass through. So 3.5 divided by 2 times pi times 0.088 is 6.33 revolutions. And then what we want to do is convert revolutions to the radians is revolutions times by 2 pi, so if we take the answer from the previous question, multiply it by 2 pi, and we get 39.77, which is approximately 40 radians. Yeah, great. Okay, so let's move on to part B. Calculate the angular speed of the drum when the mode is moving at 2.2 meters per second. So the equation you should know for this is we essentially need to divide it by V by the omega. So if the load is moving at 2.2, the drum would be rotating with a tangential speed of 2.2. So we divide it by the radius 0.88, and we'll get 2.2 divided by 0.088 is 25 radians per second. Show that for the time that the load is accelerating, the total increase in the energy of the load and the rotating parts is 5,400. So the change in energy is going to be the change in your rotational kinetic energy plus your change in GPE, and we'd also have just the change in the kinetic energy in a linear direction, because obviously the mass is also moving up with velocity. So that is going to be half times the moment of inertia, which was 7.4, times the angular speed squared, so that's 25 squared, plus it's 85 kilograms times 9.81, and then we multiply that by the height change. We also need to do half times half times 85 times 2.2 squared. And if we add all of those together, so 0.5 times 7.4 times 25 squared, plus 85 times 9.81 times 3.5, plus 0.5 times 85 times 2.2 squared, and that comes out as 5436.67, which is approximately 5,400 joules. Alright, so the constant frictional torque of 5.2 acts at the bearings of the winch. Calculate total work done by the motor to accelerate the load. So we can calculate the work done against the frictional torques. which is going to be the value of the torque times by the angular displacement. And so that's 5.2 times by 40. It was to show that question, so we can just pull out that rounded value. That's 208 joules of work. And then the work done to just in the acceleration phase, like your resultant work done, was to show that question, so we can just pull out the 5,400 joules. So then your total work is going to be these two added together, so 208 plus 5400 is 5608 joules. And we want to give this two significant figures, so it's going to be 5.6 times 10 to the 3, because this is a two significant figure number, so we're going to give it to two significant figures, which we do using standard form. Alright, let's move on. Calculate the maximum power developed by the motor. So what we need is essentially we're going to end up using this equation here. So we know it's uniformly accelerating, so we know t is a fixed value, but essentially we want to be picking out the max omega, or your maximum speed. So first thing, we need to work out what your torque is. So torque is going to be the work done divided by the angular displacement. So that was 5600 divided by 40, which was the angular displacement. So that's 140 Newton meters. So then P max is going to be 140 times 25, which is the maximum speed, which is 2,500 watts, or 3.5 times 10 to the 3, so two significant figures there. So the key thing is to recognise your maximum power will be when you're at the maximum angular speed, because torque is constant. Calculate the torque, put in your maximum angular speed, and you get your answer there. Okay, in the sport of sprint cycling, rapid acceleration is required. Discuss the importance of moment of inertia in the design of sport cycle wheels. You should explain why it's desirable to have low moment of inertia when required to accelerate, and explain the basic features of the wheel design which would lead to a low moment of inertia. And this is going to be one of the longer answer 6-mark type questions. Okay, so the first thing is going to look at, so a cyclist will have a fixed maximum torque they can apply. Because they're limited by the strength of their legs, essentially. So to have maximum acceleration, which is what you want, obviously as a cyclist you want to reach your top speed as quickly as possible if you're racing. Your moment of inertia must be minimized. And the reason for that, well, the angular acceleration, remember, is t over I. So if your t is a fixed value and you reduce your moment of inertia, that's going to increase your angular acceleration. So that's why you want it to do. You want a maximum acceleration, and the reason you want to do this, this allows you to minimize the time it takes. Oh crumbs! Can't spell. Minimize the time to reach top speed. Okay, so essentially that's why you're aiming to minimize the moment of inertia. You're trying to maximize angular acceleration, so you can minimize the time it takes to reach a top speed. So in terms of actually going about this minimization process, so remember, the moment of inertia is the sum of all the masses of your wheel times the distance from the center of rotation. So essentially, what it is a measure of how the mass is distributed. To get a low moment of inertia, you would essentially want to minimize the mass of the wheel Ugh, crumbs, not on my game today. Minimize the mass of the wheel, and the way you do that using low density material, because that would, for the same amount of material, have a smaller mass. And you would also think about and use spokes to reduce the amount of material but retain the strength. So obviously you can't have nothing going between the centre and the outside, but using spokes allows you to retain the strength in the wheel. So that in a nutshell is going through the process. The first part was explaining why a low moment of inertia is required, is because for the same torque you can achieve a higher angular acceleration, so you can therefore achieve top speed faster. You could also look at it minimises the amount of work it takes to accelerate as well in terms of angular kinetic energy or that kind of thing. And then it's explaining how the small moment of inertia is achieved by distributing the... You can't really distribute the mass closer to the centre of the wheel because you still want a wheel. So what you do is use spokes and low density materials to maintain the strength, but actually think about how you can keep the moment of inertia as small as possible. And a key thing you might want to put in here is actually linking the angular acceleration to the linear acceleration. So if the angular acceleration of the wheel is bigger, that would mean the linear acceleration is bigger as well. So that would be a nice part to add into that answer as well, I think. Alright, so on to look at an engine cycle. So we've got some various different processes, which I'm sure we'll come to. So the first thing I want to do is show that process A is isothermal. So if it's isothermal, P1 V1 should be equal to P2 V2. That is the condition of an isothermal process. So pressure at A is equal to 1 times 10 to the 5, and the volume times by 1.2 times 10 to the minus 3, and that is 1.0 times 10 to the power of 5 times 1.2 times 10 to the power of minus 3. That's 120 joules. P2 V2 is equal to, we're at B, so that's 4.8 times 10 to the minus 5 times by 0.25 times 10 to the minus 3, which is 4.8 times 10 to the minus 5 times 0.25 times 10 to the power of minus 3. Let's type that into the calculator. 0.25 times 10 to the power of minus 3, which is 120 joules also. So that condition does hold and it is isothermal. Calculate the work done by the gas in the process B2C. So during a given process, work done is going to be P delta V because pressure is constant here. So what have we got? 4.8 times 10 to the 5 times by 0.39 minus 0.25 times 10 to the minus 3. Let's calculate that. 0.39 minus 0.25 10 to the minus 3 times 4.8 times 10 to the power of 5, which comes out as equals 67.2. All the information is 2 sig fig, so we just write that as 67 joules. Okay, apply the first law of thermodynamics to determine the values of Q, W and delta U for each of the processes and for the whole cycle. Use a consistent sign convention. So the first process was isothermal, so we know that the internal energy does not change, so we can put that in there. What else do we have? We've got, what was the other process? Let's have a look back at the other. So we had an adiabatic from C to A. That would mean Q was 0 in there. Okay, so then what else? So now we should have enough information to fill in this one because we calculated this in the previous question. We've got the plus 67 in there. Using the first law of thermodynamics, we know Q is W plus delta U. So 235 minus 67 should give us the delta U here. So it does 168 because we know this Q is equal to these two added together. And let's have a look. And we can apply the same thing to the top up here. So these two should be equal to each other. So if the right hand side is equal to minus 188, so should the left hand side, applying conservation of energy. And we'd get the same here, so minus 168. Again, because Q is 0, so these two must add to 0. Therefore, we end up with this over here. So we end up with plus 47 here. Again, left and right hand side must be equal to each other. Alright, so the overall efficiency of an engine as the network output in one cycle divided by the energy supplied from heating. Okay, so let's see, the net work out is 47. We've just calculated it above, or is in the table there. And the energy supplied through heating is going to be during process B to C, because that's where the combustion occurs. So that will be this Q up here, the 235. And let's calculate that. 47 divided by 235, which is 0.2 or 20% efficiency overall there. Describe two problems that would be encountered in trying to design a real engine based on this cycle. So that might be handy to talk about the conditions of adiabatic and isothermal. So an isothermal process must run slowly, and that's because you need to allow time for heat to be exchanged to the surroundings to maintain constant temperature. But adiabatic must be very fast to allow no heat exchange during your cycle. So that's going to be very difficult to achieve. Designing an engine to change speed during a cycle is very difficult, if not impossible. So that is the issue there. So what they're looking for. So first problem, isothermal process must run very slowly. Adiabatic must run very fast. So you've kind of linked the two problems together, and the problem is designing an engine to meet both of the requirements. So that's going to be very difficult to achieve in terms of designing your engine to run. Well, you're not going to be able to do it. Okay, so question 4, moving on to look at heat engines. What is meant by the coefficient of performance of a heat pump? So it is the, well, let's write it in symbol form and then we'll explain what it means. So it's the heat delivered to the hot space divided by the work in. So let's explain this. So it's the heat delivered to the hot space, that will be the first key part, divided by the work input. Okay, and if it was a refrigerator, it would be the heat removed from the cold space, but it's not, it's being used as a heat pump, so it's the Q in or the Q delivered to the heat space, hot space. Okay, box labelled E shows a combined heat and power scheme. Provides electrical energy W from an engine-driven generator, and it also supplies Q1 to some buildings. Some of the electrical energy is used to drive the heat pump, as shown in the box, and Q2 is also used to heat buildings. You may assume that the engine runs at maximum theoretical efficiency, so that's going to be on the left where they're giving you the temperatures, and the electrical generator is 100% efficient. The output power of the engine-driven generator is 80 kilowatts. Alright, so let's have a look at the question. The fuel used in the engine is propane of calorific value 4.9 megajoules per kilogram. Calculate the flow rate of propane into the engine, stating an appropriate unit. So the first thing here is going to be calculating the efficiency, so we can work out the input power. So the maximum theoretical efficiency is going to be given by TH minus TC over TH in Kelvin. So let's dig up those values. So it's going to be 1600 minus 290 over 1600. 1600 minus 290 divided by 1600, which gives us 0.81875, yada yada yada. So P in is going to be P out divided by the efficiency, so you can actually work out how much you have to put in to get. So that was 80 kilowatts divided by 0.81 yada yada. So 80 divided by answer gives you 97.7 kilowatts. So the flow rate is going to be 97.7 times 10 to the 3 divided by the calorific value 49 times 10 to the 6. So let's times it by 1000 and divide by 49 times 10 to the power 6, which comes out at 1.99 times 10 to the minus 3. So to 2 nuclears, that's going to be 2.0 times 10 to the minus 3, and that's going to be kilograms per second, because it was megajoules per kilogram, so that's going to be in kilograms per second. Okay, the heat pump has a coefficient of performance of 2.6, so it delivers 2.6 watts for every 1 watt supplied of work. The power supplied by electrical generators to the heat pump is 16 kilowatts. So we can calculate Q in is going to be the work times by the coefficient of performance. So that's going to be 16 times 10 to the 3 times 2.6, which is 16 times 10 to the 3 times 2.6, which is 41600 watts. But we also had some energy delivered from the other system as well. So that's just from the heat pump. The Q in from the, well, let's just call it engine for better words, is going to be total power in, which was 98, divided by the useful energy. So that would give you, this is going to give you the total wasted energy, or the heat rejected. So 18 times 10 to the 3 watts. So the Q in total is going to be 41600 plus 18000, which is 59600, or it's going to be 6.0 times 10 to the 4 watts once you add that together. So the key thing in here is remembering you're getting heat not just from the heat pump, but also from the initial engine, because it was saying both Q1 and Q2 were supplied to the buildings. So you need to calculate what both of the heat rejected from each of the situation is, and then add them together to give you this final answer here. Okay. The conversion of electric energy to heat is nearly 100% efficient. Explain why the designer has proposed installing a heat pump rather than an electrical heater to provide the additional heat Q2. So a heat pump delivers more energy per unit of work input, because remember we're also taking some energy from our cold source as well, so there's two putting together. It also includes energy removed from cold source, so there's an extra supply of heat energy involved in there, and that's why you would do it. So you either put in less work, or you get more heat output for the same work. So there's two possible trade-offs there. If you want a certain amount of heat energy, you put less work using a heat engine, or for the same amount of work, you get more heat supplied. So that's the advantage there, and that concludes this paper.